Hello everyone, I'm Manny Wang. I'm glad to introduce our work AsyMo, Scalable and Efficient Deep Learning Inference on Asymmetric Mobile CPUs. This is a joint work with Shaohua Ding, done during our internship at Microsoft Research under the supervision of Ting, Yunxin, and Feng Yuan.
Deep learning technology is used extensively in mobile and edge applications, and the major deep learning players start to extend their own frameworks for mobile devices, such as TensorFlow, TensorFlow Lite, Onyx Runtime Mobile, etc.
Models in applications normally get trained on servers. For inference, because of the benefits like better privacy protection, lower latency, and reliability, on-device inference is gaining prevalence. We focus on Asymmetric CPU because it is a main computing unit for on-device inference. Mobile GPU performance is not good enough. For example, in this graph, a Snapdragon CPU outperforms other mobile accelerators in this case. Besides of the performance, the programmability issue blocks the wide usage of accelerators on mobiles. They are not generally available, lack of specs, and poor at API support. Therefore, our work focuses on improving their frame inference on mobile CPUs. Current on-device inference on mobile CPUs suffers from two common inefficiency issues. The first issue is poor performance scalability of asymmetric multiprocessor. Mobile CPUs feature an asymmetric design such as ARM Big LITTLE technology. There is a big core processor with higher CPU performance, as well as a little core processor with lower performance and energy cost. Unfortunately, as shown in this graph, trivial inference barely gains speed up by using both processors compared to just a big core processor. We also measure the average CPU usage during inference. This graph indicates that both big and little cores are seriously underutilized. The other issue is energy inefficiency from two aspects. Firstly, the OS frequency scaling is not responsive enough, especially for short-run inferences. This graph shows the measured power of carrying 970 board running MobileNet v1 inference. The inference period is marked between the two red lines. There is a mismatch between power curve and inference period. The power curve increases 34 milliseconds after the inference starts, which is 20% of total inference time. When the inference is done, the power starts to descend about 25 milliseconds later and drags a long tail to finally reach the idle power, causing a big waste of energy. The other is that mobile OS cannot identify the most energy-efficient frequency for inference tasks. It tends to set the highest CPU frequency for inference, which is good for performance rather than energy. For example, ResNet 101 consumes 81% more energy while saves only 32 inference time at the highest frequency.
We analyzed the root causes for these two issues. The first one is the unbalanced task distribution on AMP cores. Matrix multiplication takes most of the inference time. For parallel execution, MM is partitioned into sub-MM tasks. Detailed flow will be introduced later. This graph shows the number of tasks running on each core. The task distribution is unbalanced both between the big little core processor, for example, there are 89 tasks on the big cores on average, while only less than 40 tasks on little cores, and unbalanced within each processor. The second is the inferior task partition. Without proper partitioning, the performance gain from adding the little processor is still under expectation. For energy inefficiency, it is because the DVFS of mobile OS is unaware of deep learning behavior characteristics. To solve these problems, there are four major challenges. Firstly, the hardware is asymmetric. Current partitioning uses unified block size even on AMP cores, which harms performance and misleads the fair task assignment based on the number of tasks. Secondly, the cache between big and little processors are separated. Accessing remote cache can cause 5 times latency than local cache. Thirdly, there is high competition for the small cache. Existing solution like Atlas carefully determines innermost matrix for cache use. However, the high competition from multi-cores for the small cache may lead to cache thrashing. And finally, the mobile device is usually running on the interference-prone environment. Current partitioning always results in lagging threads. Convolution and fully connected operator takes most of the inference time. As shown in these graphs, both operators are implemented with matrix multiplication. Therefore, matrix multiplication is our optimization target. I will then introduce the common execution flow of MM and followed by our optimizations. The first step is to partition the input matrices into submatrices. Then, to improve the data locality, the blocks will be copied into continuous memory space. Next, the submatrix multiplication will be wrapped into a task and scheduled in a thread queue in the thread pool. The problems include, for the partition part, only consider cache size and thread number, ignoring hardware asymmetry and cost details. For the pre-copy part, there is always redundant data copy for parameter matrices. For the schedule part, existing flow ignores hardware asymmetry and data locality. This is the overview of our solution AsyMo, a novel thread pool implementation for scalable and energy-efficient DNA inference on Asymmetric mobile CPUs. Since the model is unchanged for inference, during the initialization phase, such as when the mobile app is launched, for all the MMs in the models of the app, AsyMo uses its cost-model-directed block partition strategy to work out the proper block size with the lowest time cost. For energy efficiency, AsyMo also works out the CPU frequency with the lowest energy cost based on the data reuse rate of the given model. During inference, the hardware symmetry-aware scheduler will schedule the task for big and little clusters. I will then introduce each technique in detail. We use a cost model to determine the size of the sub-MMs. This is a process of formulating the cost model. Model input are block size on each dimension, denoted as MC, KC, and NC. The output is the predicted latency total cost. Tcomp and Tmem are hardware-related parameters. The model comprehensively considers computation and memory access cost, degree of parallelism, task scheduling, and framework cost. To reduce the memory cost, we also limit block size of a task to make sure they can be held in cache. Besides, when MC equals NC, the total memory access is the least. So, cost of parallelism prefers larger blocks. The unparalleled prefers the smaller block. By scaling block size, we can find the partition with the best trade-off. Since the big and little core has different weights in the cost model, and the cache size is different, so the need to partition the blocks separately. For the input matrices, AsyMo first partitioned the longer dimension into two parts, one for the big and one for the little core cluster. The cost model is applied separately for each part. After partitioned into sub-MM tasks, these tasks will be scheduled to different threads. In our solution, each thread in the pool is pinned on one CPU core, and the task is scheduled fairly within big and little cluster. For task balance and cache locality, task stealing is allowed within a cluster or from the little core to the big core, rather than the other way around, since the big core task can be too big for little core. The above techniques solve the problem of scalability, and then we come to the energy issue. Because of the low response of OS frequency scaling, AsyMo sets the frequency directly for inference. High frequency is always good for performance but not energy. To work out the efficient frequency, a straightforward hypothesis is that memory and computation-intensive load prefers different frequency. We utilize a simplified data reuse rate to evaluate memory or computation-intensive. For Mk times Kn, the data reuse rate is as follows. Data reuse is bounded by the smallest dimension. We profile the energy and running time for CNN and RNN models at different frequency. For mobile nets, the energy keeps reducing as the running time reduces, reaching the lowest after 1.8 GHz. For RNN, the beginning part is like the normal memory-intensive behavior that time doesn't change much with frequency. But surprisingly, the running time and thus the energy dropped at high frequency. To explain the reason, we profile the random and stream memory access latency. For stream access latency, which is the left axis in dashed lines, don't change much with the frequency. But the random access latency, the solid lines, drop at certain high frequency. As energy is the combination of computation and memory access energy, for each hardware, we profile the per computation and memory access energy cost curve. Based on the data reuse rate of the given model and the energy curves, the best frequency can be set.
To evaluate the results soundly, we use different hardware, different OS, different DL framework, and different models. We all gain good improvement. One is the HiKey 970 with the Carry 970 SoC. Development board is easier for power measurement and temperature control. The other is Google Pixel 3 XL. It was the best available CPUs when doing this work. OS is Android and Debian. We implemented AsyMo in Eigen library for TensorFlow and TensorFlow Lite. The baseline is optimized TensorFlow in Lite, which is already 32% faster than default for COM-dominant models. Here is the performance scalability improvement of matrix multiplication. It is the average over a range of frequently used size. We implemented AsyMo in TensorFlow, FeatherCNN, and Onyx runtime. Each of them has different serial kernel implementation, and AsyMo can gain portable speedup on all of them. The blue line rises higher when using 8 cores compared to 4 cores, indicates the scalability is greatly improved. This shows the total performance and energy efficiency improvement. The higher, the better. First, we see when performance is the first priority and CPU frequency is set to the highest. For COM-dominant models, because of the improved CPU usage, the performance improves 48% and energy saving 22%. The FC-dominant models improve up to 1 times in inference time and 62% in energy saving. When energy is the first priority, compared to OS frequency setting, AsyMo can save 37% energy while still saving 46% of inference time for COM-dominant models, and up to 1.2 times energy saving for FC-dominant models. We break down the left graph to see the contribution of each technique. For COM-dominant models, asymmetric aware scheduling improves performance by 24%. This improvement comes from the fair task scheduling and better cache locality. Block partition improves another 24% on average. Compared to default eigen block partition, our partition cost model considers both data accesses and sequential waiting time, generates about 6 times more tasks for HOP on average. More tasks, smaller blocks, facilitate the workload balance and improve the parallelism degree. To show the portability, we also evaluate the performance improvement on Android and Debian. Android improves more because the default CPU usage is lower. Debian improves less because of the parallel execution of Linux. TensorFlow Lite result only has COM-dominant model data due to the OP support constraint. We evaluated AsyMo under some special cases. These 2 graphs shows that with background load interference and possible thermal throttling caused by continuous inference, AsyMo can still gain considerable improvements. To sum up, our work reveals the performance scalability issue due to imbalanced task distribution and energy inefficiency issue due to DVFS mismatch for mobile DL inference. Our solution, AsyMo, enables better partition, balanced scheduling, and efficient frequency setting. Experiments show great performance and energy improvement for different hardware, different OS, different DL frameworks, and different models. That's all for my presentation. Thank you.